Hello there, and welcome to Worlds Beyond Seen. I'm so glad you found your way here tonight. Whether you're settling in after a long day, lying in the quiet darkness of your room, or simply seeking a place where curiosity meets calm, you've come to the right space. Tonight, we're going to explore something that sounds like science fiction but is terrifyingly real. A story of fire in the sky, of invisible storms that could erase our modern world, and of a star that has, more than once, nearly killed everything. Before we begin our journey into the heart of solar fury, I'd like to invite you to like this video and subscribe to the channel. Your support helps us create more of these explorations into the wonders and terrors of our universe. It means the world to us, and it helps other curious minds find their way here too. Now, settle in, get comfortable, let the day's worries fade into the background, because we're about to travel back in time to a night when the sky itself seemed to catch fire, when telegraph wires glowed with phantom electricity, and when humanity got its first glimpse of just how vulnerable we really are. Part 1. The Night the Sky Caught Fire. It's September 1st, 1859. The world is a very different place than the one we know today. There are no electric lights, no telephones, no internet, no satellites orbiting overhead, but there is one technology that has revolutionized human communication, connecting continents and transforming commerce: the electric telegraph. Dots and dashes clicking across copper wires, carrying news and messages at the speed of lightning itself. It's the Victorian internet, the miracle of the age. And on this night, something impossible is about to happen. In England, a wealthy amateur astronomer named Richard Carrington is in his private observatory in Redhill, Surrey. It's just before noon on September 1st, and Carrington is doing what he does every clear day. He's observing the Sunday. Not with his naked eye, of course. That would be suicidal. He's projecting the sun's image through his telescope onto a screen where he can safely study the dark blemishes on its surface. Sunspots. Mysterious dark patches that come and go, that astronomers have been tracking for decades without really understanding what they are. Carrington is sketching these sunspots, as he does every day, recording their positions and sizes with meticulous care. The sun has been particularly active lately, covered in an unusual number of these dark marks. He's seen large groups of them, complex and tangled, sprawling across the solar surface like bruises on a golden face. And then, at 11:18 inches the morning, something extraordinary happens. A brilliant white light suddenly appears within one of the sunspot groups. It's intensely bright, even in the projected image. Carrington can barely believe what he's seeing. The light flares, brightens, then begins to fade. The entire display lasts perhaps 5 minutes, maybe a bit less. He's transfixed, watching this unprecedented phenomenon. This singular outbreak of light from the sun itself. Carrington doesn't know it yet, but he's just witnessed something that has never been recorded in human history. A solar flare, a massive explosion on the surface of the sun, releasing the energy of 10 billion atomic bombs in a matter of minutes. And that energy, that torrent of particles and radiation, is now racing toward Earth at millions of miles per hour. The journey takes just 17.6 hours. Astonishingly fast for a coronal mass ejection. Typically, these eruptions from the sun take days to reach our planet, but this one is different. This one is riding the wake of another eruption that happened days earlier, clearing a path through the solar wind like a snowplow through fresh powder. The way has been prepared, and now the main event is on its way. 17.5 hours after Carrington sees that brilliant flash, Earth's magnetic field begins to scream. It starts in the evening of September 1st and intensifies through the night and into September 2nd. Telegraph operators around the world begin reporting strange phenomena. The instruments are going haywire. Needles that should be moving smoothly are pinned to their stops, vibrating wildly. Some machines are sparking, sending showers of fire across telegraph offices. Operators receive violent electric shocks just from touching their equipment. In some cases, the telegraph paper catches fire from the induced currents. But here's the truly bizarre part. In some stations, operators discover they can disconnect the batteries that power their systems and continue sending messages anyway. The currents induced in the telegraph lines by the geomagnetic storm are strong enough to power the equipment on their own. Telegraph lines, stretching for hundreds of miles across the landscape, have become giant antennas, capturing the electromagnetic chaos and channeling it into the delicate instruments at either end. One operator in Washington, D.C., Frederick Royce, reports receiving a very severe electric shock, which stunned me for an instant. He adds that an old man sitting nearby saw a spark of fire jump from my forehead. Another operator in Pittsburgh describes streams of fire pouring from the circuits, with platinum contacts in danger of melting. The global telegraph system, the pinnacle of Victorian technology, the nervous system of modern civilization, simply stops working. From America to Europe to Australia, the wires fall silent. The world, for a few crucial hours, loses the ability to communicate across distance. It's as if someone has pulled the plug on the entire planet. But it's the sky that truly terrifies people. Starting on the night of August 28th and 29th, and then again with far greater intensity on the night of September 1st and 2nd, the aurora borealis appears in places it has no business being. The northern lights, usually confined to Arctic and subarctic regions, suddenly blaze across skies as far south as the Caribbean, in Cuba, in Jamaica, in Colombia, nearly at the equator. The entire sky is awash in curtains of red, green, and white light, pulsing and shimmering like some cosmic fire. In the Rocky Mountains, gold miners wake up at 1 a.m, see the brilliant light, and think the sun has risen. They get up, make breakfast, start their day's work. Only after an hour or so does it dawn on them that something is terribly wrong. The dawn isn't getting brighter. The light is too colourful, too restless. This isn't the sun. This is something else. In Boston, people stand in the streets reading newspapers by the light of the aurora. In Baltimore, the display is so bright that it casts shadows. A reporter in Washington, D.C., writes that the light appeared to cover the whole sky. The descriptions pour in from around the world, each more extraordinary than the last. A journalist in the San Francisco Herald writes, "The whole sky appeared to undulate something like a field of grain in a high wind. The waters of the bay reflected the brilliant hues of the aurora. Nothing could exceed the grandeur and beauty of the sight. The effect was almost bewildering and was witnessed with mingled feelings of awe and delight by thousands." From South Carolina, a woman on Sullivan's Island describes a scene that sounds biblical. The eastern sky appeared of a blood-red colour. It seemed brightest exactly in the east, as though the full moon, or rather the sun, were about to rise. It extended almost to the zenith. The whole island was illuminated. The sea reflected the phenomenon, and no one could look at it without thinking of the passage in the Bible which says, "The sea was turned to blood." The shells on the beach, reflecting light, resembled coals of fire. Many people believe the end of the world is at hand. Some think neighbouring cities are burning. The sky is so bright, so impossibly bright, that it seems the atmosphere itself must be on fire. Birds begin singing, confused into thinking dawn has arrived. Animals become restless, agitated by the strange light and the electromagnetic disturbances they can sense but humans cannot. In the southern hemisphere, the aurora australis puts on an equally spectacular show. In Chile, in Australia, in New Zealand, the sky glows with otherworldly colours. It's a global phenomenon, a planetary light show unlike anything witnessed before or since. And through it all, the telegraph system remains crippled, operators shocked and scared, equipment smoking and sparking, the copper wires themselves humming with strange electrical currents that seem to have no earthly source. Richard Carrington, back in his observatory, begins to suspect a connection. That flash he saw on the sun yesterday, and this unprecedented geomagnetic storm today, could they be related? The timing seems too perfect to be coincidence. But the sun is 93 million miles away. How could something happening there affect us here? The idea seems preposterous, and yet the evidence is hard to ignore. Carrington will write up his observations and present them to the Royal Astronomical Society. He'll be cautious, noting the correlation but refusing to claim direct causation. "One swallow does not make a summer," he'll write, displaying the scientific restraint of his era. But deep down, he suspects he's onto something profound. He's witnessed the first recorded solar flare, and he's made the first tentative connection between solar activity and terrestrial effects. The Carrington Event, as it would later be called, lasts 2 days. The geomagnetic storm gradually subsides. The telegraph system slowly comes back online. The auroras fade. Life returns to normal. But something has changed. Humanity has been given a glimpse, brief and terrifying, of the power our star wields. The sun, that benign golden disk that lights our days and warms our world, has shown its teeth. And here's the thing that should keep us awake at night. The Carrington Event, as destructive and terrifying as it was, wasn't even close to being the worst solar storm Earth has experienced. Not by a long shot. In the frozen ice of Greenland and Antarctica, in the rings of ancient trees that have stood for thousands of years, scientists have found evidence of solar storms that make the Carrington Event look like a gentle breeze. Events so powerful, so catastrophically intense, that if one struck Earth today, our technological civilization wouldn't just be damaged, it would be erased. Part 2. Understanding the Beast, what the sun really is. Before we can understand solar storms, before we can grasp the true danger our star poses to us, we need to understand what the sun actually is, because despite living our entire lives bathed in its light, despite the fact that every atom in our bodies was forged in stars like it, most of us don't really comprehend the sheer violence, the barely controlled chaos of the nuclear furnace that sits at the center of our solar system. The sun is not a gentle light bulb hanging in space. It's a roiling, churning, exploding ball of plasma, a self-sustaining nuclear bomb going off continuously, held together only by its own immense gravity. Let's start with the basics. The sun is big, stupidly, almost incomprehensibly big. If you could line up Earths across its diameter, you'd need about 109 of them. Its volume could contain 1.3 million Earths. Its mass is 333,000 times that of our entire planet. To put that in perspective, the sun contains 99.86% of all the mass in our entire solar system. Everything else, all the planets, moons, asteroids, comets, dust and gas, amounts to barely more than a rounding error. And all of that mass is pressing inward, creating pressures and temperatures so extreme that they defy normal comprehension. At the sun's core, roughly 150,000 kilometers below the surface we see, the temperature reaches 15 million degrees Celsius. 15 million degrees. At that temperature, atoms don't exist. They're torn apart. Electrons are ripped away from their nuclei. What exists at the sun's core is a soup of bare atomic nuclei and free electrons, a state of matter called plasma, the fourth state after solid, liquid, and gas. And in that hellish environment, something miraculous happens. Hydrogen nuclei, protons, moving at incredible speeds due to the extreme temperature, occasionally collide with enough force to overcome their electromagnetic repulsion and fuse together. This nuclear fusion creates helium and releases energy, a lot of energy. Every second, the sun converts about 600 million tons of hydrogen into helium, and in the process, about 4 million tons of mass is converted directly into energy, following Einstein's famous equation E equals mc squared. That energy, initially in the form of gamma rays, begins a long, slow journey outward. Here's where it gets interesting. The sun is so dense, so packed with matter, that those gamma rays can't just zip straight out. They're absorbed and re-emitted, billions upon billions of times in a process called a random walk. A single photon of light can take anywhere from 100,000 to 1 million years to make the journey from the sun's core to its surface, a journey of less than 1 million kilometers that light could otherwise cover in about 3 seconds. The sun's interior is so opaque, so resistant to the passage of radiation, that light effectively gets trapped there for millennia. By the time that energy finally emerges from the sun's surface, it has been transformed. The incredibly energetic gamma rays have been downgraded through countless interactions into the visible light and infrared radiation that we see and feel. The fury of fusion has been mellowed into the gentle sunlight that makes life on Earth possible. But gentle is a relative term when you're talking about the Sunday. The surface we see, called the photosphere, is still a hellish 5,500 degrees Celsius, hot enough to vaporize any known material instantly, hot enough that iron would not only melt but boil into gas. And this surface is not calm, far from it. The photosphere is constantly churning with convection cells called granules, each one about the size of Texas, rising and falling as hot plasma from below breaks through to the surface and cooler plasma sinks back down. It's like watching a pot of boiling water, except each bubble is larger than a continent and made of matter hot enough to ionize anything that touches it. And then there are the sunspots. Sunspots are regions where the sun's magnetic field breaks through the surface, concentrating and intensifying. These magnetic field lines inhibit convection, preventing hot plasma from rising as efficiently. As a result, sunspots are cooler than their surroundings, about 3,800 degrees Celsius instead of 5,500. That might sound odd, calling something that hot cool, but it's all relative, and because they're cooler, they appear dark against the brighter background of the photosphere. But here's the critical thing about sunspots. They're not just cosmetic features, they're symptoms of intense magnetic activity. And where you have intense magnetic activity on the sun, you have the potential for violence. The sun's magnetic field is generated by the churning, rotating plasma that makes up its interior in a process called the dynamo effect. But unlike Earth's relatively stable magnetic field, the sun's is chaotic, tangled, constantly twisting and knotting itself. And sometimes those knots become unstable. Imagine taking a rubber band and twisting it over and over. Eventually, it will snap back, releasing its stored energy all at once. Something similar happens with the sun's magnetic field. The field lines twist and build up tension, storing vast amounts of magnetic energy, and then, suddenly, they reconfigure themselves, snapping into a lower energy state and releasing all that stored energy at once. That's a solar flare. A solar flare is essentially a magnetic explosion. In a matter of minutes, the magnetic fields near a sunspot region reorganize themselves, and the energy that was stored in those fields gets converted into heat, light, and kinetic energy. Temperatures in the flare region can spike to tens of millions of degrees, even hotter than the sun's core. Particles are accelerated to near the speed of light, and electromagnetic radiation, from radio waves to X-rays to gamma rays, blasts outward in all directions. If a major solar flare happens to be pointed in Earth's direction, that radiation reaches us in just over 8 minutes, traveling at the speed of light. It can disrupt radio communications, interfere with GPS signals, and if it's strong enough, even damage satellites in orbit. But radiation, as dangerous as it is not the main threat from solar storms. The main threat comes from what often accompanies a solar flare, a coronal mass ejection, or CME. If a solar flare is a magnetic explosion, a CME is an eruption. When the sun's magnetic field lines snap and reconfigure, they can sometimes fling vast amounts of plasma, gas, and embedded magnetic fields out into space. We're talking about billions of tons of matter, traveling at speeds anywhere from a few hundred to a few thousand kilometers per second. A CME is not radiation. It's actual matter, hurled off the sun like a colossal cannonball of superheated gas and magnetic fields. And if one of these monsters hits Earth, it doesn't just deliver electromagnetic radiation. It slams into our planet's magnetic field and temporarily distorts it, compresses it, tangles it up, That's what causes the aurora. Those beautiful lights in the sky are actually the visible signature of our atmosphere being bombarded by high-energy particles from the Sunday. The particles follow Earth's magnetic field lines down toward the poles, where they collide with atoms and molecules in the upper atmosphere, exciting them and causing them to emit light. Oxygen produces green and red colors. Nitrogen produces blue and purple. The result is a light show that has awed humans for millennia, but beneath that beauty is violence. Those same particles that create the aurora can induce electrical currents in anything conductive: power lines, pipelines, railroad tracks, and in the 19th century, telegraph wires. The sun operates on cycles. The most famous is the 11-year solar cycle, a rise and fall in the number of sunspots that has been observed since telescopes first revealed them. During solar minimum, the sun can go days or even weeks with no visible sunspots. The surface appears calm, quiet, almost serene. During solar maximum, the sun can be covered in sunspot groups, with flares and CMEs erupting regularly. But these cycles are not entirely predictable. Some solar maxima are intense, others are relatively weak, and occasionally the sun does something completely unexpected, a flare far more powerful than the cycle would suggest, a CME far faster and more massive than the average. These are the events that can change history. The Carrington Event occurred during a solar maximum, but it was unusual even by those standards. The sunspot group that produced it was enormous, and the flare and subsequent CME were exceptional. But the sun is capable of far worse. How do we know this? Because the sun, for all its power, is actually a fairly typical star. And when we look at other stars like it, scattered across the galaxy, we see them doing things our sun hasn't done in recorded history. We see them unleashing flares thousands of times more powerful than anything we've measured from our own star. These are called superflares, and their existence raises a terrifying question. If other stars like the sun can produce superflares, then presumably so can the sun itself. It's just a matter of time, of waiting long enough, of observing long enough. And when we look at the evidence locked in ice and trees, evidence that goes back thousands of years beyond human records, we discover that the sun has indeed unleashed superflares, multiple times. And when it did, the consequences for Earth were, well, we'll get to that. But first, let's finish our journey back in time to September 1859 to see exactly what Richard Carrington and his contemporaries experienced when the sky caught fire. Part 3. Telegraph operators and burning wires. To truly understand what happened during the Carrington Event, to grasp the sheer chaos and terror of those September nights in 1859, we need to understand the telegraph system, because in 1859, the telegraph wasn't just a communication tool. It was the infrastructure of modern civilization. It was how business was conducted, how news spread, how the world stayed connected. And when it failed, civilization itself seemed to teeter on the edge. The electric telegraph had only been in widespread use for about 15 years when the Carrington Event struck. Samuel Morse had demonstrated his first working system in 1844, and by 1859, telegraph lines crisscrossed North America and Europe. Over 200,000 kilometers of copper wire stretched across landscapes, connecting cities and towns, spanning oceans via undersea cables. It was the Victorian Internet, a phrase that's more apt than it might first appear. Before the telegraph, information traveled at the speed of a horse or a ship. A message from New York to San Francisco took weeks. News from Europe took longer. But with the telegraph, information could span a continent in seconds. The world had shrunk. Distance had been conquered, or so it seemed. The telegraph operated on a simple principle. An operator would press a key, completing an electrical circuit. A small current would travel down the wire to a receiving station, where it would cause a needle to move or a sounder to click. A trained operator could translate the patterns of clicks into letters and words using Morse code. It was elegant, efficient, and revolutionary. But it had a vulnerability that no one had anticipated. Those long copper wires stretching for miles across the countryside, were perfect antennas for capturing electromagnetic disturbances. And on the night of August 28 to 29, 1859, and again with far greater intensity on September 1 to 2, those wires became conduits for chaos. The first warnings came on August 28th. Telegraph operators in various cities began reporting unusual behavior from their instruments. The needles were fluctuating wildly, making it difficult to send or receive messages. Some operators reported feeling tingling sensations when touching their equipment. Strange, but not entirely unprecedented. Telegraph lines had been disrupted before by thunderstorms and by previous auroral displays. But what happened on September 1st and 2nd was of a completely different magnitude. E. W. Colgan, a telegraph manager in Pittsburgh, provided one of the most detailed reports. He described how the instruments were completely overridden by powerful currents that seemed to have no terrestrial source. The needles were pinned against their stops, vibrating with such force that there was genuine concern they might break. Platinum contacts, designed to handle the normal low currents of telegraph operation, were in danger of melting, and perhaps most disturbingly, he observed streams of fire pouring from the circuits, actual fire, from the telegraph wires. In Bealeton, Virginia, the aurora was so bright at 1 a.m. that it woke sleeping birds. Larks began to warble, thinking dawn had arrived. A conductor on the Orange and Alexandria Railroad, also awake and perhaps frustrated by the disruption to his schedule, reportedly shot 3 of them. It's a small, strange detail in the historical record, but it speaks to how unsettling the phenomenon was. The natural order had been upended. Night had become day, or something close to it. Telegraph offices in Boston reported that operators could disconnect the batteries that normally powered their systems and continue sending messages anyway. The induced currents in the telegraph lines were strong enough to transmit signals without any artificial power source. It was as if the Earth itself had become a giant battery, pumping electricity through the wires. In Washington, D.C., Frederick Royce was at his telegraph station when he received a shock violent enough to stun him. An elderly gentleman sitting nearby watched in amazement as a visible spark jumped from Royce's forehead. Think about that for a moment. A visible electrical discharge from a man's head caused by currents induced in telegraph wires by a storm on the sun, 93 million miles away. Other operators reported similar experiences: severe shocks, sparks. In some cases, the telegraph paper, soaked in chemicals to make the marks left by the receiving stylus visible, caught fire. There are reports of several telegraph offices having small fires that had to be quickly extinguished. In Norway, a telegraph operator named Gleason managed, through clever manipulation of the sporadic currents, to maintain communication with another station for several hours without any battery power whatsoever. He would later describe it as one of the strangest experiences of his professional career, sending messages through what seemed like pure magic, through electricity that came from nowhere and everywhere at once. The transatlantic telegraph cable, a marvel of Victorian engineering that had only been in operation for a year, fared better than land-based lines, probably because undersea cables are naturally shielded by seawater. But even it experienced disruptions and unusual current patterns. Across the Atlantic, European telegraph systems were similarly affected. In France, operators reported the same phenomena: wild fluctuations, shocks, sparking equipment. In England, some telegraph lines remained functional by disconnecting their batteries and relying solely on the induced earth currents. It was discovered, quite by accident, that the direction of these currents would reverse periodically following the pulsations of the aurora overhead. The global nature of the disruption was unprecedented. This wasn't a local thunderstorm taking out a few lines. This was every telegraph system on Earth, from America to Europe to Australia, all experiencing the same chaos at the same time. The first truly global technological disaster. But while telegraph operators struggled with their malfunctioning equipment, ordinary people were witnessing something far more viscerally terrifying. The sky itself seemed to be on fire. The auroral displays of September 1 to 2, 1859, were visible across an astonishing range of latitudes. From Norway to Australia, from Cuba to Chile, people saw the lights. And these weren't the subtle, ghostly curtains of green that typically characterize the northern lights. These were blazing, blood-red sheets of light that covered the entire sky. In many reports from lower latitudes, the dominant color was red. This is significant. Red auroras occur at higher altitudes than the more common green ones, and they indicate that the storm has penetrated deeper into Earth's atmosphere. Oxygen atoms at altitudes of 200 to 300 kilometers emit red light when excited, whereas the familiar green comes from oxygen at 100 to 200 kilometers. A predominantly red aurora is a sign of a truly major storm. From the Rocky Mountains, the story of the gold miners who woke up thinking it was morning has become legendary. Imagine their confusion. You wake up, see bright light through your tent or cabin window, assume it's dawn, start your day, make coffee, begin preparing breakfast, and then, gradually, you realize something is wrong. The light isn't changing. It's not getting brighter, not fading. It's pulsing, shifting, moving in ways sunlight never does. And when you step outside, instead of the golden glow of sunrise, you see the entire sky rippling with red and green flames. One miner, interviewed years later, said he had initially thought the aurora was a massive forest fire, and he and his companions had begun preparing to evacuate before they realized the light was coming from above, not from the surrounding mountains. In Boston, citizens stood in the streets, reading newspapers by the auroral glow. The light was bright enough for that, genuinely bright enough to read by at midnight. People held impromptu gatherings, marveling at the spectacle, arguing about what it could mean. Some thought it was a sign from God. Others, more scientifically inclined, suspected some kind of atmospheric electricity, though the mechanism was completely unknown. A journalist in Charleston, South Carolina, wrote one of the more poetic descriptions. The eastern sky appeared of a blood-red color. The whole island was illuminated. The sea reflected the phenomenon, and no one could look at it without thinking of the passage in the Bible which says, "The sea was turned to blood." The shells on the beach, reflecting light, resembled coals of fire. That biblical reference wasn't unusual. Many people, especially in the more religious communities of the time, interpreted the aurora as a divine sign. Some feared it was a portent of the end times. Ministers preached sermons about it. Newspapers ran religious interpretations alongside the scientific speculation. But perhaps the most telling detail is how many people initially thought their neighboring towns or cities were on fire. The red glow on the horizon, the flickering light, the overall brightness, it all suggested a massive conflagration. Fire departments in several cities were reportedly alerted by concerned citizens convinced that something terrible was burning nearby. In Cuba, where auroras are essentially unknown, the sight must have been absolutely terrifying. Indigenous peoples and colonists alike had no cultural framework for understanding such a phenomenon. The sky had simply gone insane, washing out the stars with sheets of colored light. From Chile, reports described the aurora australis, stretching across the entire southern sky. From Australia, similar accounts. This was a truly global event, visible from both hemispheres simultaneously, which meant the geomagnetic disturbance was affecting the entire planet. Scientists and astronomers around the world scrambled to make observations, though most were caught completely off guard. Richard Carrington, having witnessed the solar flare the previous day, was in the unique position of being able to draw a tentative connection, but even he was unsure. The idea that the sun could reach across 93 million miles of void and affect Earth's magnetic field and atmosphere seemed almost absurd. Other astronomers and physicists, however, had noticed something else. Magnetometers, instruments designed to measure Earth's magnetic field, had gone haywire. At the Kew Observatory in London, the physicist Balfour Stewart had been monitoring the observatory's magnetometers. On the morning of September 1st, right around the time Carrington observed his solar flare, Stewart noticed a sudden, sharp disturbance in the magnetic readings, what he called a magnetic crochet, a sudden kink in the otherwise smooth variations of Earth's field. Then, about 17 hours later, when the coronal mass ejection reached Earth, the magnetometers went completely off scale. The needles were pinned at their maximum deflections. The magnetic disturbance was so severe that the instruments literally couldn't measure it accurately. This was the first truly scientific measurement of a geomagnetic storm, and it provided crucial evidence for the Sun-Earth connection that Carrington suspected. Stewart's data, combined with Carrington's observation of the solar flare and the reports of telegraphic disturbances and auroras, painted a picture that was hard to dismiss. Something on the Sun had triggered something on Earth. Somehow, across the vast gulf of space, our star had reached out and touched our planet. In the days following the storm, newspapers around the world reported on the phenomena. The New York Times, the Times of London, the San Francisco Herald, newspapers in Paris, Berlin, Sydney, all carried accounts of the spectacular auroras and the telegraphic disruptions. Artists tried to capture the beauty of the lights. Scientists tried to explain them. The public simply tried to understand what had happened. The explanation, when it finally came, would take decades to fully develop. The mechanism by which solar activity affects Earth wouldn't be completely understood until well into the 20th century, until we developed a comprehensive understanding of plasma physics, magnetic fields, and the structure of the Sun's atmosphere. But the Carrington Event had planted a seed. It had shown, in the most dramatic way possible, that we live in a dynamic solar system, that the Sun is not a constant, unchanging source of light and warmth, but an active, variable star capable of affecting its planetary neighbours, and that our technology, our infrastructure, is vulnerable to cosmic forces beyond our control. In 1859, the damage was relatively limited. Telegraph systems were disrupted for hours or days, but they were repaired. Some equipment was damaged or destroyed, but it was replaced. The economic impact, while significant, was manageable. But imagine if the same event happened today. Part 4. Richard Carrington and the first solar flare. Richard Carrington deserves more recognition than he typically receives. He was not a professional astronomer in the modern sense. He didn't have a university position or conduct research for a living. Instead, he was a wealthy amateur, a man of independent means who could afford to pursue his passion for astronomy without needing to earn a living from it. Born in 1826 to a wealthy London brewery owner, Carrington had the education and resources that came with his class. He attended Trinity College, Cambridge, though he didn't particularly distinguish himself academically. He showed an early interest in astronomy, but his father expected him to join the family brewing business. Richard, however, had other ideas. He was fascinated by the sky, by the movements of the planets and stars, and particularly by the Sunday. In 1852, after his father's death, he inherited enough money to pursue astronomy full-time. He set up a private observatory in Redhill, Surrey, equipped with a fine refracting telescope and other instruments. His primary interest was the sun, specifically sunspots. These dark blemishes on the solar surface had been observed for centuries, but systematic study of them was still relatively new. Carrington saw an opportunity to make a real contribution to science by carefully tracking the positions, sizes, and movements of sunspots over time. Every clear day, weather permitting, Carrington would project an image of the sun onto a screen and sketch the sunspots he saw. He would note their positions relative to the solar equator, their sizes, their shapes, their groupings. Over years of observation, he accumulated a massive data set on solar activity. This might sound tedious, and honestly, it probably was, but it was also valuable. Carrington was building a long-term record of solar behavior that could be used to search for patterns, for cycles, for any kind of regularity in the sun's activity. He was doing the grinding, patient work that all good science requires. And then came September 1st, 1859. Carrington was at his telescope at 11:18 a.m. projecting the sun's image as usual. The sun was heavily spotted at the time. Multiple groups of sunspots dotted the disk, larger and more complex than average. He was sketching one particularly large group when something extraordinary happened. 2 points of intensely bright white light appeared within the sunspot group. Carrington later described them as 2 patches of intensely bright and white light. They appeared suddenly, blazed with incredible brilliance for about a minute, then began to fade. The entire event lasted perhaps 5 minutes. Carrington was stunned. He'd been observing the sun almost daily for years and had never seen anything like this. The bright spots were clearly not reflections or artifacts of his telescope. They were features on the sun itself, appearing and disappearing in real time as he watched. He immediately called for a witness, someone to verify what he was seeing, but by the time anyone else arrived, the spots had faded. He was left alone with his observations, his sketches, and the certain knowledge that he'd witnessed something unprecedented. Another observer, Richard Hodgson, independently observed the same event from his location in London. Hodgson's report, which he prepared separately from Carrington's, described the same bright patches, the same timing, the same intensity. This independent confirmation was crucial. It meant that what Carrington had seen was real, not an artifact or an illusion. Both men reported their observations to the Royal Astronomical Society in November 1859. Their papers were published side by side in the Society's monthly notices. Carrington's report was cautious, even skeptical. He noted the appearance of the bright spots, the timing of the subsequent geomagnetic storm, and the obvious correlation between the 2 events, but he refused to claim direct causation. "One swallow does not make a summer," he wrote. "The scientific method demands caution, and Carrington was being properly scientific. A single coincidence, no matter how striking, doesn't prove a connection. You need repeated observations, statistical evidence, a mechanism." But privately, Carrington suspected he was onto something profound. He'd seen a solar eruption, and less than a day later, Earth had been hit by a massive geomagnetic storm. The timing was too perfect. The coincidence was too striking. Balfour Stewart's magnetometer data provided additional support. Stewart had observed a sudden disturbance in Earth's magnetic field, his magnetic crochet, at the exact time Carrington saw the bright spots on the Sunday. Then, 17 hours later, came the major geomagnetic storm. The sequence was clear. Solar event, immediate magnetic disturbance, delayed major storm. The scientific community of the time didn't immediately accept the connection. Many astronomers and physicists were skeptical. How could something happening on the sun affect Earth? What was the mechanism? The sun was 93 million miles away. That's an almost incomprehensible distance, a void of empty space. How could an event on the sun's surface reach across that emptiness and affect our planet? We didn't have the concept of plasma yet, or of coronal mass ejections, or of the solar wind. We didn't understand that the sun is constantly ejecting particles into space, creating a tenuous but real connection between itself and its planets. We didn't know about Earth's magnetosphere, that bubble of magnetic field that surrounds our planet and shields us from the worst of solar radiation. All of those discoveries would come later, in the early to mid-20th century. In 1859, the idea of a Sun-Earth connection was novel, even radical. But Carrington had planted the seed. He'd made the first observation of a solar flare, and he'd tentatively suggested a connection to terrestrial effects. Over the following years, as more geomagnetic storms occurred and more astronomers observed the sun, the evidence accumulated. It became clear that there was indeed a correlation between solar activity and geomagnetic disturbances. Sunspot-rich periods were associated with more frequent auroras and magnetic storms. Quiet solar periods saw fewer such events. By the early 20th century, the connection was accepted as fact, even if the mechanism remained mysterious. Scientists knew that the sun somehow affected Earth's magnetic environment, but the details were murky. Carrington continued his solar observations until 1861, when personal tragedy struck. His wife died suddenly, and Carrington, devastated, abandoned his astronomical work. He remarried, sold his observatory, and spent his final years in obscurity. He died in 1875, just 49 years old, largely forgotten by the scientific community. It wasn't until much later, as the study of solar-terrestrial relations developed into a mature science, that Carrington's contributions were fully recognized. The 1859 event was named the Carrington Event in his honor. His careful observations and his tentative but prescient suggestion of a Sun-Earth connection are now seen as foundational to the field of space weather. But here's the thing that should scare us. The Carrington Event, for all its drama and significance, was not a uniquely powerful storm. It was the biggest one we've observed with instruments. It was the one that happened to occur when we had just enough technology to be disrupted by it, but not so much that it would cause catastrophic damage. If the Carrington Event had occurred a century earlier, when there were no telegraphs, no electrical systems at all, it would have been nothing more than a spectacular light show. People would have marveled at the auroras, perhaps feared them, but there would have been no tangible damage, no infrastructure to disrupt. If it occurs a century later, in the mid-20th century, the damage would have been far worse. Power grids, radio communications, early computers, all vulnerable to geomagnetic disturbances. And if it happens today, in our hyper-connected, satellite-dependent digital world, we'll get to that nightmare scenario shortly. But first, we need to go back even further in time, before telegraphs, before written records, to storms that make the Carrington Event look gentle. Part 5. Before Carrington, Ancient Solar Storms, written in ice and trees. The Carrington Event is the largest solar storm in recorded history. But recorded history, when it comes to detailed instrument-based observations, only goes back a few centuries. The first telescopic observations of the Sun began in the early 1600s. Systematic sunspot observations, like Carrington's, are even more recent. But the Sun is 4.6 billion years old. It has been there, burning and erupting and sending out storms for an almost incomprehensible span of time. And Earth has been here, orbiting in its path for nearly as long, which raises an obvious question. What did the Sun do before we were here to watch it? The answer is written in ice and wood. When a solar storm strikes Earth, it doesn't just create auroras and disrupt electronics. It has more subtle effects that can persist for years, decades, even millennia. One of these effects involves carbon-14. Carbon-14 is a radioactive isotope of carbon. It's constantly being produced in Earth's upper atmosphere when cosmic rays, high-energy particles from space, collide with nitrogen atoms. These collisions produce carbon-14, which then mixes into the atmosphere as carbon dioxide, gets absorbed by plants, eaten by animals, and generally becomes part of the global carbon cycle. Archaeologists and geologists use carbon-14 for radiocarbon dating, a method of determining the age of organic materials. The principle is simple. Living things constantly exchange carbon with their environment, so they have a certain level of carbon-14 inches their tissues. When they die, that exchange stops, and the carbon-14 begins to decay. By measuring how much carbon-14 is left, you can calculate how long ago the organism died. But here's the interesting part. The amount of carbon-14 inches the atmosphere isn't constant over time. It varies based on how many cosmic rays are hitting Earth. And the number of cosmic rays hitting Earth varies based on several factors, one of which is solar activity. When the Sun is active, when it's throwing out solar wind and magnetic fields, it actually shields Earth from some cosmic rays. The solar wind creates a bubble around the solar system that deflects galactic cosmic rays, reducing the amount that reaches Earth. When the Sun is quiet, more cosmic rays get through, and more carbon-14 is produced. But there's another effect, a more dramatic one. When a truly massive solar storm hits Earth, it brings with it high-energy particles that can create carbon-14 directly in sudden, sharp bursts. These solar energetic particles smash into the atmosphere and trigger the same reactions that cosmic rays do, but in far greater numbers and in a very short period of time. The result is a spike in carbon-14 production, a sharp increase that gets incorporated into plants and tree rings and eventually preserved in the organic materials of that time period. Trees are particularly useful for detecting these spikes because they grow in annual rings. Each year, a tree adds a new ring of growth, and the carbon in that ring reflects the atmospheric carbon of that year. By carefully analyzing tree rings going back hundreds or thousands of years, scientists can measure the carbon-14 levels year by year and look for anomalies. And they've found them. In 2012, a Japanese physicist named Fusa Miyake was analyzing tree rings from ancient Japanese cedar trees. She was looking at carbon-14 levels, and she found something strange. In the year 774, or 775 AD, there was a sudden, dramatic increase in carbon-14. The spike was enormous, far larger than any known variation in the regular carbon cycle. It represented a sudden influx of cosmic radiation into Earth's atmosphere, a pulse of high-energy particles that had no obvious source. Miyake's discovery was published in the journal Nature and immediately sparked intense interest and debate. What could have caused such a spike? A supernova? A gamma-ray burst from a distant neutron star? Some unknown astronomical event? The most likely explanation, though one that was initially hard to accept, was a massive solar storm. A solar energetic particle event orders of magnitude more powerful than anything observed in modern times. An event that made the Carrington Event look small by comparison. Further research confirmed the finding. Scientists examined tree rings from around the world, from Europe, North America, and other regions, and found the same carbon-14 spike in the years 774 to 775 AD. It was a global event, not a local anomaly, and they found similar spikes in ice cores, where beryllium-10 and chlorine-36, other isotopes produced by cosmic radiation, showed sharp increases in the same time period. The evidence was overwhelming. Around 774 or 775 AD, Earth was hit by a massive burst of solar radiation. The storm would have been at least 10 times more powerful than the Carrington Event, possibly much more. But here's the disturbing part. There are no written records of this event. The year 775 AD was right in the middle of the early medieval period. Civilizations around the world were keeping written records, yet there's no mention of spectacular auroras or any other unusual phenomena. Well, that's not quite true. Some researchers have combed through historical texts and found a few tantalizing hints. The Anglo-Saxon Chronicle, a record of English history, mentions a red crucifix seen in the sky after sunset in 774 AD. Could this have been an aurora? Possibly, but the description is vague and could refer to many things. There are other scattered reports from around the world that might relate to the 774 AD event, but nothing definitive. Nothing that describes the global auroral displays and widespread disruption that the Carrington Event produced. Why not? Why would an event 10 times more powerful than Carrington not be recorded? One possibility is that the 774 AD event, while releasing massive amounts of radiation, didn't produce a major geomagnetic storm. Not all solar events are the same. A storm could release huge numbers of energetic particles without necessarily producing the kind of magnetic disturbance that causes bright auroras. The particles would interact with the upper atmosphere, creating carbon-14, but the effects at ground level might be relatively muted. Another possibility is that the record simply didn't survive, or that the event was recorded but in ways we don't recognize or haven't found yet. The early medieval period was a time of transition and turmoil in many parts of the world. Written records were often lost or destroyed, but the mystery deepens, because 774 AD is not the only Miyake event. In 2013, Fusa Miyake and her colleagues published another discovery. They'd found a second carbon-14 spike, this time in the years 993 to 994 AD. Again, Tree rings from around the world showed the same pattern. Again, ice cores confirmed it with beryllium-10 spikes, another massive solar storm, smaller than the 774 AD event, but still several times larger than Carrington, had struck Earth. And again, there's very little in the historical record. The year 993 AD saw no widespread reports of spectacular auroras or other unusual phenomena. It's as if these massive storms came and went, leaving their signature in the carbon cycle but barely touching human consciousness. Since those initial discoveries, researchers have found more Miyake events, one around 660 BC, another around 5259 BC, another around 5410 BC, another around 7176 BC, and most recently, in 2023, researchers identified what appears to be the largest Miyake event ever found, a carbon-14 spike around 12,350 BC, roughly 14,300 years ago. This ancient event, found in subfossil trees recovered from the banks of the Druzette River in the French Alps, shows a carbon-14 increase twice as large as the 774 AD event. That makes it roughly 20 times more powerful than the Carrington event, possibly more. 20 times more powerful. Try to wrap your mind around that. The Carrington event, which disrupted global telegraph systems and created auroras visible from the tropics, was a hiccup compared to this prehistoric monster. These Miyake events tell us something uncomfortable. They tell us that the sun is capable of unleashing storms far more powerful than anything we've observed in the modern era. They tell us that while such storms are rare, perhaps one every few centuries or so, they are not impossible. They're part of the sun's natural behavior, and they tell us that we are utterly, catastrophically unprepared for such an event. Because here's the thing, none of the Miyake events would have had much impact on pre-industrial human civilizations. They might have created spectacular auroras, perhaps causing wonder or fear, but there would have been no infrastructure to damage, no power grids to overload, no satellites to fry, no GPS systems to disrupt. The humans who experienced these storms might have told stories about them, passed down legends of the night the sky burned, but otherwise, life would have continued. Not so today. Today, a Miyake event would not just disrupt our civilization, it would devastate it. And the terrifying reality is that we wouldn't have much warning. A few hours, maybe a day or two at most. Not nearly enough time to brace for impact, to shut down vulnerable systems, to prepare for a technological dark age that could last months or years. But before we explore that nightmare scenario, we need to understand something else. We need to understand that Miyake events might not even be the worst the sun can do. Because when we look at other stars like the sun, we see something even more terrifying. We see superflares. Part 6. The Miyake events. When the sun went supernova, almost. The Miyake events represent a class of solar storms so powerful that they challenge our understanding of what the sun can do. These are not just bigger versions of the Carrington event. They are fundamentally more energetic, more intense, more catastrophic. Let's break down what we know about them. The 774 to 775 AD event, the first to be discovered, shows a carbon-14 increase of approximately 1.2%. That might not sound like much, but in the context of the carbon cycle, it's enormous. It represents a sudden, massive influx of high-energy particles into Earth's atmosphere, far beyond anything cosmic rays normally produce. By analyzing the size and distribution of the carbon-14 spike, scientists can estimate the energy of the solar storm that produced it. The numbers are staggering. The 774 to 775 AD event released something like 1045 to 1046 ergs of energy. To put that in perspective, the Carrington event released maybe 1043 ergs. That's 100 to 1,000 times less. We're talking about a storm that, if it hit today, would deliver a radiation dose to satellites and spacecraft that would be instantly lethal to any electronics not specifically hardened against such events. Astronauts in space would receive a radiation dose that, while not immediately fatal, would pose serious health risks. But the radiation is only part of the story. If a Miyake event produced a coronal mass ejection of proportional strength, and we have every reason to believe it would, the geomagnetic effects would be catastrophic. Think about what the Carrington Event did to telegraph systems in 1859. Now imagine that same magnetic disturbance amplified by a factor of 10 or more. The induced currents in power lines would be massive. Transformers would overheat and fail. Power grids across entire continents would collapse within minutes. Satellites in orbit would be bombarded by radiation and electromagnetic interference. Many would simply stop functioning. Their electronics would be fried, their solar panels damaged by the intense particle flux, their orbits destabilized by the sudden expansion of Earth's atmosphere caused by the storm heating the upper layers. GPS satellites, which our modern world relies on for everything from navigation to financial transactions to precision agriculture, would be particularly vulnerable. Even if the satellites themselves survived, the ionospheric disturbances caused by the storm would render GPS signals useless for days or weeks. Communication satellites would face similar problems. The infrastructure of global telecommunications, which depends on satellites in both geostationary and low Earth orbits, would be severely degraded or knocked out entirely. And then there's the internet, the backbone of modern civilization. Most long-distance internet traffic travels through undersea fiber optic cables, which are generally considered safe from solar storms. Fiber optics don't conduct electricity, so they shouldn't be affected by induced currents, right? Wrong. The problem is the equipment at either end of those cables, and the equipment that amplifies signals along the way. That equipment is electronic, powered by electricity, and vulnerable to power surges and electromagnetic interference. If the power grids feeding those systems fail, or if the equipment is damaged by induced currents in nearby power lines, the internet goes down. The 993 to 994 AD Miyake event appears to have been smaller than the 774 to 775 event, but still far larger than Carrington. And the prehistoric events, particularly the one from 14,300 years ago, were larger still. The 14,300-year-old event is particularly intriguing because it occurred during the late Paleolithic, a time when anatomically modern humans were well established around the world, but were still living as hunter-gatherers. They would have seen incredible auroras, possibly visible even in equatorial regions, but they would have left no written records. Only the trees remember. What's most disturbing about the Miyake events is how little we understand about them. We know they happened. The carbon-14 and beryllium-10 evidence is incontrovertible, but we don't know exactly what caused them. The leading theory is that they were massive solar flares, accompanied by equally massive coronal mass ejections. But there are problems with this explanation. For one thing, the sun doesn't seem energetic enough. Based on its size, temperature, and magnetic field strength, models suggest the sun shouldn't be able to produce flares more than about 100 times larger than the biggest ones we've observed. But the Miyake events seem to require flares thousands of times larger. Some researchers have proposed alternative explanations. Could the Miyake events have been caused by supernovas? Unlikely, because a supernova close enough to cause such effects would have left other evidence, like elevated levels of various isotopes, that we don't see. Gamma ray bursts from distant neutron stars, also unlikely for similar reasons. Magnetized neutron stars flaring in our galactic neighborhood? Possible, but there's no other evidence for such events. The most recent research suggests that the Miyake events were indeed solar in origin, but that they represent a type of solar activity we don't fully understand. Perhaps a series of flares occurring in rapid succession, a kind of solar storm of storms that releases energy in bursts over days or weeks. Perhaps a mechanism involving the sudden release of magnetic energy stored in the sun's interior, something that happens very rarely but very catastrophically. Whatever the cause, the Miyake events prove one thing beyond doubt. The sun is capable of far more violence than the Carrington event demonstrated, and that violence is not a relic of the distant past. It's part of the sun's ongoing behavior. Rare, yes, but not impossible. In fact, when you start looking at the statistical distribution of solar storms, a disturbing picture emerges. We've observed solar storms for only about 400 years since the invention of the telescope. In that time, we've seen one Carrington-class event. That's a sample size of 1, which tells us essentially nothing about how often such events occur. But when we include the Miyake events we can detect in tree rings and ice cores going back thousands of years, we get a better picture. And that picture suggests that Carrington-class events probably happen once every century or two. Major Miyake events probably happen once every 500 to 1,000 years, which means we're overdue. The last confirmed Miyake event was in 993 AD, over 1,000 years ago. If these events do indeed have a recurrence interval of roughly 500 to 1,000 years, then statistically, we're in the danger zone right now. The next one could be decades away, or it could be tomorrow, and we have no way of predicting it, no way of seeing it coming with more than a day or two of warning, no way of preparing our infrastructure to withstand such a storm. But it gets worse, because when we look beyond the Miyake events, when we look at what other stars like the Sun are doing, we see something even more frightening. We see superflares. Part 7. Other stars, other storms, superflares in the cosmos. Our Sun is a very typical star. It's a G-type main sequence star, often called a yellow dwarf, though it's neither particularly yellow nor particularly small. It sits comfortably in the middle range of stellar masses, temperatures, and luminosities. For every characteristic you can measure, size, age, composition, rotation rate, the Sun is boringly average. This is actually a good thing for us. Extreme stars make lousy hosts for life. Very massive stars burn too hot and die too quickly. Very small stars are prone to violent flares and might lock their planets into tidal synchronization, leaving them roasted on one side and frozen on the other. But medium-sized stars like the Sun, they're stable, long-lived, predictable. Or so we thought. The advent of space-based telescopes like Kepler and TESS, designed primarily to find exoplanets, has given us an unprecedented view of the behavior of stars across the galaxy. These telescopes monitor thousands of stars simultaneously, measuring tiny variations in their brightness over months and years. And in those variations, they've found something disturbing. They've found stars like the Sun producing flares thousands of times more powerful than anything our Sun has produced in recorded history. These are called superflares, and they challenge our assumptions about stellar behavior. A typical solar flare releases about 1032 ergs of energy. A large flare might reach 1033 ergs. The flare, Carrington observed, which triggered the largest geomagnetic storm in recorded history, was probably around 1033 to 1034 ergs. A superflare releases 1035 ergs or more. Some exceed 1036 ergs. That's 100,000 times more energy than the flare that caused the Carrington event. When the Kepler Space Telescope first started detecting superflares in 2012, astronomers were initially skeptical. These events were so energetic that it seemed impossible for a Sun-like star to produce them. Superflares were thought to be the domain of young, rapidly rotating stars with extremely strong magnetic fields, not middle-aged, slowly rotating stars like ours. But the data was clear. Kepler was observing Sun-like stars, stars with similar mass, temperature, and age to our Sun, experiencing flares of unprecedented power. The rate of occurrence was low, maybe one superflare per century or per millennium for any given star, but they were definitely happening. At first, there was hope that these super-flaring stars might be subtly different from the Sun in some crucial way. Maybe they were slightly more massive, or slightly younger, or had stronger magnetic fields due to faster rotation. If that were true, it would mean the Sun couldn't produce superflares, and we'd be safe. But as more data accumulated, that hope faded. The superflaring stars covered a wide range of stellar properties, and many were essentially indistinguishable from the Sunday. Some were even older and more slowly rotating than the Sun, which should make them less magnetically active, not more. The inescapable conclusion is that stars like the Sun, including possibly the Sun itself, can produce superflares. It's just a matter of probability and time. Now, here's where things get truly terrifying. If a superflare from the Sun hit Earth, it wouldn't just knock out our technology, it would potentially threaten the biosphere itself. A superflare would be accompanied by a massive burst of ultraviolet and X-ray radiation. This radiation would hit Earth in about 8 minutes, traveling at the speed of light. The ozone layer, which protects us from harmful solar UV, would be severely depleted, not destroyed entirely, but thinned enough that surface UV levels could become dangerous to living things. Agricultural crops would be affected. Phytoplankton in the oceans, which form the base of the marine food web and produce a large fraction of Earth's oxygen, could be harmed. The immediate effects might not be catastrophic, but the disruption to ecosystems could be severe. Then, hours or days later, the coronal mass ejection would arrive, and if the superflare has released 100,000 times more energy than the Carrington flare, we can expect the CME to be proportionally massive. The geomagnetic storm that followed would be beyond anything humanity has ever experienced. Every power grid on Earth would be at risk. The induced currents would be so large that transformers would not just fail, they'd be destroyed, melted, physically ruined. And here's the thing about power transformers. They're not something you can quickly replace. These are massive, custom-built pieces of equipment, often weighing hundreds of tons each. They're manufactured by specialized companies, with lead times of months or even years. If a superflare destroyed transformers across multiple continents simultaneously, there literally wouldn't be enough spare transformers on the planet to replace them all. Parts of the world could be without electricity for months or years. Think about what that means. Modern civilization is entirely dependent on electricity. We use it for everything: water pumping and treatment, food refrigeration and distribution, hospitals, communications, banking, transportation. If the power went out for weeks or months, the consequences would be catastrophic. Cities would become unlivable, water supplies would fail, food would spoil, medical facilities would be overwhelmed, and without communications, coordination of any recovery effort would be nearly impossible. Some estimates suggest that a Carrington-class event, if it hit today, could cause $2 trillion in economic damage and leave tens of millions of people without power for extended periods. A superflare event could be 100 times worse. The economic damage would be measured in tens of trillions of dollars. The loss of life could be in the millions. And this is not just speculation. In 2012, Earth had a very close call. On July 23rd of that year, the Sun released a massive CME, a Carrington-class event, possibly even larger. The CME roared through space at incredible speed. If it had hit Earth, we'd be living in a very different world right now. But it missed. By about 9 days. 9 days of Earth's orbital motion. If the CME had erupted a week earlier, we would have been directly in its path. Our satellites would have been fried. Our power grids would have been severely damaged. The 2012 event could have been the disaster that ended the modern technological age. We dodged a bullet, and most people never even knew it happened. Daniel Baker, a space weather expert at the University of Colorado, said of the 2012 event, if it had hit, we would still be picking up the pieces. Other scientists have called it the most powerful solar storm in 150 years, possibly since the Carrington event itself, and we missed it by pure luck, by the simple accident of where Earth happened to be in its orbit at that moment. This is what keeps solar physicists and space weather experts up at night. We know these massive storms happen. We know they can hit Earth. We know they would cause unimaginable damage to our technological civilization. And we know that we have very little ability to predict them more than a day or two in advance, and almost no ability to defend against them when they do come. The Sun is not our enemy. It's the source of all our energy, the reason life exists on Earth at all. But it's also a massive ball of barely controlled nuclear fury, and sometimes that fury escapes in ways that can reach across 93 million miles and touch us. We like to think of our modern world as advanced, as sophisticated, as nearly invulnerable. We've split the atom, we've walked on the moon, we've sent probes to the edge of the solar system. We feel powerful, in control, but we're not. We're incredibly vulnerable. A storm from the sun, an event that happens naturally and inevitably over long enough timescales, could send us back to the pre-electrical age in a matter of hours, and we wouldn't be prepared for it. We've built our entire civilization on the assumption that the electrical grid will always work, that satellites will always be there, that communications will always function. We've created countless single points of failure, systems that have no backup, no redundancy, no way to function if the electricity goes out. And we've done this while living under a star that is fully capable of wiping out all of it. The question is not if another major solar storm will hit Earth. The question is when, and whether we'll be ready. Part 8. Our fragile modern world. What would happen today? Let's walk through it. Let's imagine, in detail, what would happen if a Carrington-class solar storm hit Earth today. Not a superflare, not a Miyake event, just a regular Carrington-class storm, the kind that happens maybe once a century. The scenario begins on the Sunday. A large, complex sunspot group appears on the solar disk, facing Earth. Solar observers notice it immediately. It's big, active, unstable. Within hours, it releases a powerful X-class flare, the largest classification we have. The electromagnetic radiation from the flare, X-rays, ultraviolet, radio waves, hits Earth in 8 minutes. Radio blackouts occur on the day side of the planet. High-frequency communications, the kind used by aircraft and ships, suddenly go silent. GPS signals become unreliable. Satellite operators notice anomalies in their systems. But that's just the warning shot. The flare is accompanied by a coronal mass ejection, a billion-ton blob of magnetized plasma racing toward Earth at maybe 2,000 kilometers per second. Fast, but not the fastest we've seen. Space weather forecasters see it coming. They have maybe 12 to 24 hours to warn the world. Alerts go out. Power companies put their grids on high alert. Satellite operators begin moving their spacecraft into safe modes. Airlines reroute flights to avoid polar routes where radio communications will be disrupted and radiation exposure will be higher. Astronauts on the International Space Station take shelter in the most shielded part of the station, and then the CME arrives. It hits Earth's magnetosphere like a hammer. The protective magnetic bubble that surrounds our planet compresses, distorts, writhes under the assault. The bow shock, the boundary where the solar wind meets our magnetosphere, is driven inward, sometimes nearly to the altitude where satellites orbit. Particles from the solar wind, channeled by Earth's magnetic field lines, pour into the upper atmosphere near the poles. The sky explodes in color. Auroras blaze across the northern and southern reaches of the planet, green and red and purple, brighter than anyone alive has ever seen. In North America, the northern lights are visible as far south as Texas. In Europe, they reach the Mediterranean. In the southern hemisphere, they touch South Africa and Australia. It's beautiful, terrifying, but beautiful. And then the power starts failing. The geomagnetic storm induces electrical currents in long conductors, anything that stretches across the landscape, power lines, pipelines, railway tracks, and especially power transmission lines. These induced currents, called geomagnetically induced currents, or GICs, flow into power transformers. Transformers are designed to handle alternating current at specific voltages and frequencies. They're not designed to handle these low-frequency DC-like currents. The GICs cause the transformer cores to saturate, to reach their magnetic limits. When that happens, the transformers start to heat up rapidly. The internal temperature rises, the insulation begins to break down, and in the worst cases, the transformer can be permanently damaged or destroyed. One by one, transformers across the grid begin to fail. Protective systems, designed to prevent cascading failures, start automatically disconnecting parts of the grid. But this just causes more problems, shifting load to other transformers, which then also fail. Within minutes, the power grid begins to cascade toward total failure. It's not a simple blackout where you can just flip switches to bring things back online. It's a systemic collapse, with damage to critical infrastructure. The first reports come from Scandinavia and Canada, areas at high latitude where the geomagnetic effects are strongest. Then from the northern United States. Then from Scotland, northern England, Germany. Entire cities go dark. Hospitals switch to backup generators, but those aren't designed to run for weeks. They'll run out of fuel in days. Water treatment plants lose power. Without electricity, the pumps fail, and water pressure drops to zero. Within hours, cities have no running water. Food in refrigerators and freezers begins to spoil. Grocery stores, which depend on just-in-time delivery systems, start running out of supplies. Gas stations can't pump fuel without electricity. Even if you have a car, you can't fill it. But it's worse than just losing electricity. Remember, this is the 21st century. We depend on satellites for everything. Navigation, communications, financial transactions, the precise time synchronization that underlies the internet and cell phone networks. And those satellites are getting pummeled by the solar storm. The radiation levels in orbit are off the scale. Satellite systems, even those designed to withstand space weather, are being overwhelmed. Some satellites go into safe mode, shutting down non-critical systems to ride out the storm. Others simply fail, their electronics fried by the radiation. GPS satellites, orbiting at 20,000 kilometers altitude, are right in the crosshairs. Some fail completely. Others provide wildly inaccurate data as the ionosphere, disturbed by the storm, refracts and distorts their signals. Within hours, GPS is essentially useless. Navigation systems stop working. Ships at sea lose their guidance. Aircraft already in flight divert to the nearest airports. All scheduled flights are grounded. But it's not just about getting from point A to point B. The entire modern logistics system depends on GPS. Delivery trucks use it. Shipping containers are tracked with it. Even precision agriculture, which requires GPS to guide tractors and equipment, grinds to a halt. Communication satellites in geostationary orbit, 36,000 kilometers up, are equally vulnerable. Some lose contact with ground stations. Others, damaged by the radiation, begin to tumble or drift out of their designated positions. Telephone and internet services that depend on satellite links start failing. Remote regions that rely entirely on satellite communications are completely cut off. Even in major cities, cell phone networks, which depend on precise time signals from GPS to coordinate between towers, start experiencing problems. The internet backbone, which depends on a complex interplay of fiber optic cables, electronic switching equipment, and satellite links, begins to fragment. Some regions lose connectivity entirely. Others experience severe slowdowns as traffic is rerouted through damaged or congested nodes. Financial markets, which require precise time synchronization for trading and which depend on satellite communications for global coordination, go haywire. Stock exchanges around the world shut down, unable to operate reliably. Electronic banking systems, already stressed by the power outages, become unreliable. Credit card systems fail. ATMs stop working. Within 24 hours, the global economy is on the verge of collapse. But the storm isn't done yet. Geomagnetic disturbances can last for days, pulsing and fluctuating as successive waves of solar plasma hit Earth's magnetosphere. Each pulse induces more currents, causes more damage to vulnerable systems. Emergency services are overwhelmed. With communications spotty and transportation systems crippled, coordinating any kind of response is nearly impossible. Hospitals, running on backup power, have to start rationing care. Police and fire departments struggle to respond to emergencies. Governments try to maintain order, but without communications, without electricity, Without the basic infrastructure of modern life, their ability to govern is severely limited. And remember, this is just a Carrington-class event. This scenario assumes a storm roughly equivalent to what happened in 1859. It would be bad, potentially catastrophic for modern civilization, but it would be recoverable, eventually. The bigger question is, how long would recovery take? For the power grid, the answer depends on how many transformers were damaged. If it's just a few, replacement might take weeks or months, but if it's hundreds or thousands, we're talking years. And during that time, large regions of the world would be without reliable electricity. The economic cost is almost impossible to calculate. A 2008 report from the National Academy of Sciences estimated that a Carrington-class event today could cause $1.2 trillion in damage just in the United States. That's about 10% of annual GDP. The global cost could easily be twice that or more, but the human cost would be worse. In the modern developed world, we've built our entire way of life on the assumption of reliable electricity and communications. Take those away for months, and society begins to break down. Cities, which depend on constant inflows of food, water, and fuel, would become unlivable. People would flee to rural areas, but those areas wouldn't be able to support the influx. Famine, disease, civil unrest, all of these would become very real possibilities. Some estimates suggest that in a prolonged grid-down scenario, such as a year-long blackout across major portions of the United States, the death toll could reach into the millions, not from the solar storm itself, but from the cascading effects of losing our technological support system. And all of this is from a moderate solar storm, one that we know has happened before and will almost certainly happen again. Now imagine a Miyake event, a storm 10 or 20 times more powerful. The damage wouldn't just be 10 or 20 times worse, it would be qualitatively different. Catastrophic doesn't begin to describe it. Such a storm wouldn't just damage our infrastructure, it would annihilate it. Power grids would be unsalvageable. Satellite constellations would be devastated. Communications would be knocked back to pre-electronic levels, and the recovery time wouldn't be measured in months or years, but in decades. Some scientists have speculated that a direct hit from a Miyake event could literally send human civilization back to the 19th century. Not metaphorically, literally. We'd lose almost everything that makes the modern world modern. And here's the truly terrifying part. There's essentially nothing we can do to stop it. We can't control the sunday, we can't deflect a coronal mass ejection, we can't prevent a solar flare from occurring. All we can do is prepare. And right now, we're woefully unprepared. Part 9. The ones we missed, near misses, and future threats. The 2012 event, the one that missed us by 9 days, wasn't the only close call we've had. Over the past few decades, as our ability to monitor space weather has improved, we've detected numerous powerful solar storms that either just missed Earth or grazed us at an angle. In March 1989, a strong geomagnetic storm struck Earth. It wasn't Carrington level, but it was significant. In Quebec, Canada, the power grid failed within 90 seconds of the storm's arrival. 6 million people were left without electricity for 9 hours. Some areas were dark for days. The cause was transformer failure due to geomagnetically induced currents, the same mechanism that would be triggered by a larger storm, just on a smaller scale. Repair costs ran into the hundreds of millions of dollars, and this was from a storm that was maybe 1/10 the strength of the Carrington event. In October 2003, a series of powerful solar flares, dubbed the Halloween storms, disrupted satellite operations, caused radio blackouts, and created spectacular auroras visible from unusual latitudes. Airlines rerouted flights to avoid polar routes. NASA had to turn off several scientific instruments temporarily to prevent damage. In May 2024, Earth was hit by a G5 storm, the first extreme geomagnetic storm in over 20 years. It disrupted GPS systems, caused problems with precision agriculture equipment, and created stunning auroral displays visible from Mexico and Puerto Rico. Satellites in low Earth orbit experienced increased atmospheric drag, requiring orbital adjustments. It was a warning shot, a reminder that we're always one solar flare away from serious trouble. But we've been lucky. Most major solar storms in recent decades have either missed Earth entirely or struck at angles that reduced their impact. The Sun can emit coronal mass ejections in any direction, and Earth is a relatively small target. The odds that any given CME will hit us directly are actually quite low, maybe 1 in 50 or so. But it's a numbers game. Over time, the odds catch up with you. There's also the question of what we call the magnetic vulnerability period. The most severe geomagnetic effects occur when a CME's magnetic field is oriented opposite to Earth's. When that happens, the two magnetic fields can connect through a process called magnetic reconnection, allowing solar wind particles to pour directly into our magnetosphere. But if the CME's magnetic field is parallel to Earth's, the effects are much weaker. The storm is deflected, like a rock glancing off a shield instead of striking it dead on. Which way a CME's magnetic field is oriented is essentially random. We can't predict it until the CME is almost on top of us. This means that even if we see a massive CME heading our way, we won't know how bad the storm will be until it's too late to do much about it. This uncertainty makes space weather forecasting incredibly difficult. We can see solar flares happen, we can detect CMEs leaving the Sun and estimate their speed and direction, but we can't say with certainty whether any given CME will cause a major geomagnetic storm until about an hour before it arrives. An hour. That's our warning time for a disaster that could cost trillions of dollars and disrupt global civilization for years. And there's another factor that makes this even scarier. We don't fully understand the Sun's long-term behavior. The 11-year solar cycle is well documented. We can predict, with reasonable accuracy, when the Sun will be at solar maximum and when it will be at solar minimum. But within those cycles, there's enormous variation. Some solar maxima are very active, with numerous large flares and CMEs. Others are relatively quiet. Some solar minima are deep and prolonged, with the Sun almost free of spots for months. Others are shallow and brief. And then there are longer-term variations. The Maunder minimum, a period from roughly 1,645 to 1,715, saw exceptionally low solar activity. Sunspots were rare. Auroras were almost never seen. It coincided with the Little Ice Age, a period of cooler global temperatures, though whether the two were related is still debated. The point is, the Sun is variable on timescales that exceed human lifetimes and even historical records. We have good data on solar activity for maybe 400 years since the invention of the telescope. That's nowhere near long enough to understand the full range of the Sun's behavior, which brings us back to the Miyake events and the question they raise. Are these one-time freak occurrences statistical outliers that happen once every few millennia? Or are they part of a pattern, a predictable, if rare cycle of solar violence? We don't know. We have maybe 9 confirmed Miyake events spread over 15,000 years. That's not nearly enough data to draw firm conclusions about their frequency or causes. What we do know is this. The Sun is capable of producing storms far more powerful than anything we've directly observed. These storms have happened in the past. They will happen in the future. And when the next one occurs, our response will determine whether we face a temporary setback or a civilizational collapse. The scary truth is that we're probably not as prepared as we should be. There are plans, yes, protocols for responding to severe space weather, but these plans are largely untested, and they assume a level of warning and coordination that might not be possible in a real crisis. Some critical infrastructure has been hardened against geomagnetic storms. Some transformers have been equipped with protective devices. Some satellites have been built with more robust shielding, but much of our infrastructure remains vulnerable. Why? Because hardening systems against solar storms is expensive, and the storms are, in any individual year, unlikely. It's hard to justify spending billions of dollars to protect against a threat that might not materialize for decades. It's the classic problem of preparing for low probability, high-impact events. We're terrible at it as a species. We tend to react to disasters after they happen, not to prevent them before they occur. But with solar storms, we might not get the chance to learn from our mistakes, because if the next big one is a Miyake event or worse, there might not be much left of our technological civilization to rebuild. Part 10. Watching the Sun, How We Monitor Our Star. Despite the threats, despite our vulnerability, we're not completely blind to the dangers the Sun poses. Over the past few decades, we've developed an increasingly sophisticated system for monitoring solar activity and forecasting space weather. It starts with ground-based solar observatories. Telescopes around the world observe the Sun daily, tracking sunspots, monitoring the solar magnetic field, looking for signs of instability that might presage a flare, or CME. These observatories use specialized instruments, H-alpha telescopes that see the Sun in a specific wavelength of light, revealing features like prominences and filaments, magnetographs that measure the strength and orientation of magnetic fields on the solar surface, coronagraphs that block the bright disk of the Sun to reveal its faint outer atmosphere, the corona, where CMEs originate. But ground-based observations have limitations. Earth's atmosphere distorts solar images and blocks many wavelengths of light that would be useful for studying the Sunday, which is why we've put telescopes in space. The Solar and Heliospheric Observatory, SOHO, launched in 1995, revolutionized our understanding of the Sunday. Positioned at the L1 Lagrange point, a gravitationally stable location between Earth and the Sun, SOHO has provided 24/7 observations of solar activity for nearly 3 decades. SOHO can see the Sun in multiple wavelengths, from visible light to extreme ultraviolet to X-rays. It can detect coronal mass ejections as they leave the Sun and track their movement through space. It has discovered thousands of comets as they plunge toward the Sunday, and it has given us continuous, real-time data on solar activity, allowing us to monitor the Sun like never before. The Solar Dynamics Observatory, SDO, launched in 2010, took things even further. SDO captures images of the Sun every 12 seconds in 10 different wavelengths. Its spatial resolution is incredibly high, allowing scientists to see features just a few hundred kilometers across on the solar surface. SDO has shown us the Sun in unprecedented detail. The churning convection cells on the surface, the twisted magnetic fields that form sunspots, the explosive violence of solar flares, which can release in minutes the energy the Sun normally produces in days, the sinuous, snake-like shapes of coronal mass ejections as they erupt from the solar atmosphere. There's also the STEREO mission, twin spacecraft that orbit the Sun ahead of and behind Earth, giving us a stereoscopic view of solar activity. If a CME erupts from a region of the Sun not facing Earth, STEREO can see it and give us advance warning that it might sweep by us. And, perhaps most importantly, there's the Parker Solar Probe, launched in 2018. Parker is doing something no spacecraft has ever done before. It's flying directly through the Sun's outer atmosphere, the corona, skimming just a few million miles from the surface. Parker is measuring the solar wind at its source, trying to understand how the Sun's magnetic field and plasma dynamics create the flow of particles that fills the solar system. It's providing data that will help us understand not just what the Sun does, but why it does it. And that understanding is crucial for predicting space weather. On the ground, we have a network of magnetometers scattered around the world, constantly measuring Earth's magnetic field. When a geomagnetic storm strikes, these instruments detect it immediately, providing real-time data on the storm's strength and evolution. We also have networks of GPS receivers that monitor the ionosphere, the layer of Earth's atmosphere that affects radio communications and satellite navigation. Disturbances in the ionosphere caused by solar storms show up as errors in GPS signals, giving us another way to track space weather effects. All of this data feeds into space weather forecasting centers. In the United States, the primary agency responsible is NOAA's Space Weather Prediction Center in Boulder, Colorado. Similar centers operate in Europe, Japan, and other countries. These centers analyze incoming data, run computer models, and issue forecasts and alerts. When a major solar flare occurs, they can issue a warning within minutes. When a CME is detected heading toward Earth, they can estimate its arrival time and potential impact. But space weather forecasting is still an immature science. We can see storms coming, but we can't predict them with the same accuracy we can predict terrestrial weather. The timescales are too short, the data too sparse, the physics too complex. A weather forecast telling you it will rain 3 days from now is useful. You can plan around it. But a space weather forecast giving you 24 hours warning of a major geomagnetic storm, that's helpful, but it's not nearly enough time to fully protect vulnerable infrastructure. What we really need is earlier warning, days in advance, not hours. And that requires better observations, better models, and better understanding of the sun's behavior. Some proposals have been made for a constellation of satellites positioned around the sun, giving us a 360-degree view of solar activity. This would allow us to see CMEs from any angle, not just those aimed directly at Earth. Combined with improved models of how CMEs propagate through space, this could give us several days of warning instead of just one. But such a system would be expensive, requiring multiple spacecraft and years of development. And it's not clear that governments are willing to make that investment for a threat that is, in any given year, relatively unlikely. There's also ongoing research into better understanding the sun's magnetic field and the processes that lead to flares and CMEs. If we could predict when a particular sunspot region is about to erupt, we could give even earlier warnings. Some scientists are exploring machine learning and artificial intelligence techniques, training algorithms on decades of solar observations to recognize patterns that precede major eruptions. Early results are promising, but we're still far from having a reliable prediction system. The bottom line is this: we've made enormous progress in understanding and monitoring the Sunday. We're no longer flying blind, as humanity was in 1859, but we're also not as prepared as we need to be for a truly major solar storm. We have warning systems, but limited warning time. We have some hardened infrastructure, but much remains vulnerable. We have plans for responding to space weather emergencies, but those plans are largely untested in a real crisis. And most importantly, we have very limited ability to predict when the next major storm will occur. We know it's coming, eventually. We just don't know if it will be next year or next century. Part 11. Can we survive? Preparation and protection. So what can we do? Are we simply at the mercy of the sun, hoping that a major storm doesn't hit during our lifetimes? Or is there a way to prepare, to harden our infrastructure, to ensure that when the next big one does hit, we can ride it out? The answer is yes, but it's complicated and expensive. Let's start with the power grid, which is probably our most critical vulnerability. Geomagnetically induced currents are well understood. We know how they form, we know what damage they cause, and we know how to mitigate them. The most effective protection is to install devices called GIC blockers or neutral blocking devices. These are essentially DC current limiters that prevent geomagnetically induced currents from entering the transformer windings. They allow the normal AC current to flow but block the low-frequency currents induced by geomagnetic storms. Installing these devices on key transformers, particularly at vulnerable high-latitude locations, would significantly reduce the risk of grid failure. It wouldn't eliminate the risk entirely. A truly massive storm could still cause problems, but it would make the grid much more resilient. The problem? Cost. There are thousands of transformers in the U.S. power grid alone, and GIC blockers aren't cheap. Protecting every vulnerable transformer could cost billions of dollars, and power companies, which operate on thin profit margins, are understandably reluctant to make such investments without a clear mandate. Some countries have begun taking this seriously. Finland, which is at high latitude and particularly vulnerable to space weather effects, has invested heavily in grid protection. They've installed monitoring systems and protection devices at key nodes in their grid. When a major geomagnetic storm is forecast, they can take proactive measures, temporarily disconnecting vulnerable equipment or shifting power flow to reduce the strain. The United States has been slower to act, though there has been progress. The North American Electric Reliability Corporation, NERC, has developed standards for geomagnetic disturbance preparedness. Some utilities have installed GIC monitoring equipment and protection devices, but it's a patchwork effort. Some parts of the grid are reasonably well protected, others remain highly vulnerable, and there's no comprehensive, nationwide plan for ensuring grid resilience against severe space weather. Satellites are another major vulnerability, and they're even harder to protect. You can't just install a protective device on a satellite that's already in orbit. Whatever protection it has must be built in from the start. Modern satellites are generally more robust than their predecessors. Designers have learned from previous solar storms and have incorporated better shielding, more redundant systems, and the ability to shut down non-critical functions during severe space weather. But there's a limit to how much you can harden a satellite. More shielding means more weight, which means a more expensive launch, and some components, particularly solar panels and sensitive instruments, can't be fully shielded without making them non-functional. The best protection for satellites is operational, monitoring space weather forecasts and putting satellites into safe mode when a major storm is coming. This reduces the power flowing through sensitive electronics, which reduces the risk of damage from induced currents or radiation. But this only works if you have sufficient warning. And as we've discussed, our warning time for major solar storms is measured in hours, maybe a day or two at most. There's also the question of satellite constellations. Companies like SpaceX are launching thousands of small satellites for global internet coverage. These satellites orbit at relatively low altitudes, where atmospheric drag is still significant. During a major geomagnetic storm, the upper atmosphere heats up and expands, increasing the drag on low-orbit satellites. In May 2024, SpaceX lost dozens of Starlink satellites because a geomagnetic storm caused them to experience more drag than expected, causing their orbits to decay faster than they could compensate for. If a major Miyake-class event occurred, hundreds or even thousands of low-orbit satellites could be lost in a matter of days. Replacing that many satellites would take years and cost billions of dollars. And in the meantime, services that depend on those satellites, internet, communications, Earth observation, would be severely disrupted. For critical infrastructure on the ground, there are other measures that can help. Burying power lines, for example, reduces but doesn't eliminate their vulnerability to geomagnetically induced currents. Diversifying power sources and creating more localized grids with smaller, independent systems could reduce the risk of cascading failures. Communication systems can be made more resilient by maintaining backup systems that don't rely on satellites or electricity. Old-fashioned ham radio, which requires minimal power and can operate independently, could be crucial for emergency communications during a major grid-down event. Governments and organizations have developed emergency response plans for severe space weather. FEMA in the United States has solar storm scenarios in its disaster planning. The Department of Homeland Security has issued guidelines for critical infrastructure operators, but plans are only as good as their implementation. And in a real crisis, when communications are disrupted, when power is out, when satellite systems are offline, it's not clear how effective any plan would be. There's also a psychological dimension. People in modern developed countries have lived their entire lives with reliable electricity and communications. The idea of living without those things, even temporarily, is almost unthinkable. Yet that's exactly what could happen in a major solar storm. Preparing people for such an event, ensuring they understand the risks and know what to do, is just as important as hardening infrastructure. And it's arguably even harder because it requires changing mindsets and behaviors. Some researchers have proposed more radical solutions. One idea is to develop rapid response mobile transformers that could be quickly deployed to areas where grid transformers have failed. These wouldn't be permanent replacements, but they could provide temporary power while damaged equipment is being repaired or replaced. Another proposal is to develop better forecasting capabilities. by establishing a permanent space weather monitoring station at the L5 Lagrange point, a position in Earth's orbit about 60 degrees behind our planet. From there, a spacecraft could see CMEs erupting from the Sun's western limb from Earth's perspective, and provide up to 5 days of advance warning before those CMEs reach Earth. This extra warning time would be invaluable. 5 days would allow power companies to take defensive measures, satellite operators to prepare their systems, airlines to adjust flight plans, and the public to be alerted and prepared. But again, this requires investment. A spacecraft at L5, with the necessary instruments and communication systems, would cost hundreds of millions of dollars, and it would need to be maintained and eventually replaced. The fundamental question is, how much are we willing to spend to protect against a threat that might not materialize for decades or even centuries? It's a question without an easy answer. On one hand, the potential damage from a major solar storm is enormous, possibly trillions of dollars. Spending a few billion on protection seems prudent by comparison. On the other hand, there are many threats facing humanity, and resources are finite. Money spent on solar storm protection can't be spent on climate change mitigation, pandemic preparedness, or any number of other pressing needs. Ideally, we'd address all of these threats, but in reality, we have to make choices, and those choices are shaped by politics, economics, and the very human tendency to ignore low-probability threats until they actually happen. What's needed, perhaps more than anything, is awareness. Most people have never heard of the Carrington Event. They don't know what a solar storm is or what damage it could cause. They're not aware that our modern technological civilization is vulnerable to events beyond our control. If more people understood the risk, if there were more public pressure to take space weather seriously, governments and companies might be more willing to invest in protection. Because here's the thing, we can prepare for this. The technology exists. The knowledge exists. What's lacking is the will and the resources. And every year we delay, every year we put off making those investments, we roll the dice a little more. Eventually, the sun will throw another major storm our way. Eventually, our luck will run out. The question is, will we be ready? Part 12. Living under an unpredictable star. As we come to the end of this journey through solar fury and human vulnerability, it's worth stepping back and asking a bigger question. What does it mean to live under an active star? The sun is not a light bulb. It's not a stable, unchanging source of energy. It's a massive ball of roiling plasma, driven by nuclear fusion, wrapped in complex and ever-shifting magnetic fields. It's dynamic, violent, and to some degree, unpredictable. And yet, it's also the source of all our warmth, all our light, all the energy that drives life on Earth. Every photon of sunlight that warms your skin took hundreds of thousands of years to make the journey from the sun's core to its surface, then just 8 minutes to reach Earth. Every calorie of food you eat came ultimately from sunlight captured by plants. Even the fossil fuels that powered the Industrial Revolution were ancient sunlight, stored in plant matter and transformed over millions of years. We owe everything to the Sunday our existence, our civilization, our future. And that same sun, that benevolent giver of life, is capable of erasing everything we've built in a matter of hours. It's a paradox at the heart of the human condition. We are utterly dependent on forces we cannot control and can barely predict. We build our cities, our technologies, our entire way of life on the assumption that certain things will remain constant, that the sun will rise each day, that its light will be steady, that its fury will remain contained. But those assumptions are fragile. The sun will do what the sun will do, and we are, despite all our technological prowess, still at its mercy. The Carrington Event and the Miyake events are reminders of that fundamental truth. They show us that the universe is not tame, not safe, not designed for our comfort. We live in a cosmos that is, at its core, indifferent to our existence. But they also show us something else, our resilience. Humanity has been hit by solar storms before, including storms far more powerful than Carrington, And we survived. We adapted. We learned. The people who lived through the 774 AD Miyake event didn't understand what was happening to them. They saw auroras, perhaps, and told stories about them, but they didn't have the knowledge we have now. They couldn't have understood that they were witnessing a cosmic storm from their star. Yet they carried on. They lived their lives, raised their children, built their civilizations. The storm passed, and humanity endured. We have advantages they didn't. We understand the threat. We can see it coming, at least sometimes. We have the technology to protect ourselves, if we choose to use it. But we also have vulnerabilities they didn't. Our civilization is far more complex, far more interconnected, far more dependent on systems that can fail catastrophically. The telegraph operators of 1859 could ride out the storm because the damage was limited, localized, repairable. Could we do the same today? That's the question we're going to have to answer, sooner or later. Because the sun is not done with us. It will flare again. It will erupt again. And eventually, one of those eruptions will be aimed directly at Earth. When that day comes, we'll find out whether we've learned from the past, whether we've prepared for the future, or whether we've been too complacent, too focused on the present to think about the threats that live beyond our atmosphere. Living under an active star means accepting uncertainty. It means understanding that despite all our knowledge, despite all our technology, there are forces in the universe that we cannot predict and cannot control. But it also means something else. It means appreciating the delicate balance that allows us to exist at all. The sun could be far more active than it is. Some stars, similar to ours, produce superflares regularly, not once every few millennia, but once every few years. If the sun were one of those stars, life on Earth would be impossible. Instead, we got lucky. We have a star that is, for the most part, stable and well-behaved. Its violent outbursts are rare enough that life has had time to evolve, to spread, to become complex and eventually conscious. But rare is not the same as never, and as we've seen, the sun has shown us, repeatedly throughout history, that it is capable of violence on a scale that could threaten our existence. So what do we do with that knowledge? We could live in fear, constantly worried about the next solar storm, the next cosmic disaster. But that seems like a terrible way to live. Fear, unchecked, becomes paralysis. Or we could ignore the threat, assume it won't happen in our lifetimes, and carry on as if we're safe. But that seems dangerously naive. The history written in ice and trees tells us that major solar storms do happen, and they happen more often than we'd like to think. Perhaps the answer is somewhere in between. We acknowledge the threat, we take reasonable precautions, we harden our most critical infrastructure, we develop better monitoring and forecasting capabilities, we make plans for responding to emergencies, and then we get on with our lives. We build, we create, we explore, we push the boundaries of knowledge and technology, we look outward to the stars and inward to the mysteries of consciousness. We live, knowing that our existence is temporary, that our civilizations rise and fall, that everything we build will eventually crumble, but we live anyway, because that's what conscious beings do. We create meaning in an indifferent universe. The Carrington Event, in a strange way, shows us both our vulnerability and our strength. It shows us that we are small, fragile, living at the mercy of cosmic forces. But it also shows us that we are resilient, adaptive, capable of understanding and preparing for threats that our ancestors couldn't even imagine. We stand at a unique moment in history. We're the first generation of humans to truly understand the sun, to see it not as a god or a simple light source, but as a complex, dynamic, sometimes dangerous star. And we're the first generation to have built a technological civilization so advanced and yet so vulnerable that a storm from that star could threaten our entire way of life. What we do with that knowledge will determine our future, whether we take the threat seriously and prepare for it, or whether we ignore it and hope for the best. The sun will make its choice eventually. It will erupt again, massively and violently. The only question is, when it does, will we be ready? Thank you for joining me on this journey through the history of solar storms, from the spectacular terror of the Carrington Event to the hidden fury of the Miyake events, from the near misses of recent decades to the terrifying possibility of superflares. I hope this has given you a new appreciation for the star we orbit, for its power and its unpredictability. And I hope it's given you a new appreciation for how fragile our modern world really is, built as it is on the assumption that the sun will always be gentle, always be kind. Sleep well tonight, under the glow of our unpredictable star. And when you see the sun rise tomorrow morning, remember, it's not just a light in the sky. It's a massive nuclear furnace, burning with a fury that has shaped our world and could, if we're not careful, reshape it again. Until next time, this is Worlds Beyond Seen. Stay curious, stay humble, and keep looking up.